Hello and welcome with another video. Today I'm here with another topic again, something new, something more interesting and exciting, which I hope you will be enjoying today. Today we are going to have a little, talk about cis and trans isomerism. Okay, cis and trans, right? This is another new term. As we are nowadays dealing with stereochemistry, so let's discuss cis-trans isomerism, right? So referring to the bonding regarding alkenes, it has other mind-blowing results, right? There are compounds having 4 carbons, right? Alkenes can describe, okay, that is what? Of course, butenes, yes. One butene or 2 butene, as butenes has isomeric forms. We all know that butene exists in the isomeric forms, as in unbranched carbon chains, the chains that has a double bond both at one end, both either at one end or just in the middle of the chain. It has the double bond, right? So as in 1 butene or in 2 butene, these are the two very simple examples of cis-trans isomerisms that we are going to mention. So the 2 butenes, that is the isomeric alkenes that are differentiated by the position of double bond, which I just mentioned, are called the constitutional isomers. These are also called constitutional isomers. Now, I'm Professor Dr.Mchem from Dr.Mchem Institute of Chemistry, University of St. Jamshur, and I hope you all know me very well. So, I'm here again with this very interesting topic, that is cis-trans isomerism. So, let's start with cis-trans isomerism. Cis-trans isomerism. So the 2-butene, now we were just talking about the 2-butene molecule, right? So the 2-butene, it exhibits another way that is very essential type of isomers, that is butene has 2 different forms. One with the, if you talk about butene, it exists in 2 different forms. Okay, now the 2 forms, one has the boiling point around 3.7 degrees centigrade. One of them has boiling point around 3.7 degrees centigrade, whereas the other one has 0.88 degrees centigrade. Now the 2 forms, one has this one, that is 3.7 degrees centigrade, whereas the other one has 0.88 degrees centigrade. Now the compound that has the greater boiling point is called the cis-2-butene. That is this one. It's referred to as cis-2-butene. Okay, the compound with a greater boiling point is called cis-2-butene, whereas or Z2-butene. Now cis-2-butene, or you can also call it, I will write it with another color, cis-2-butene or Z2-butene, one and the same thing. Now I will let you know what is Z stands for. Why the cis form is also called Z form, I will let you know in a minute. So the compound that has a greater boiling point is called cis-2-butene or Z2-butene. That is, now if you look at the model, I have a beautiful molecular model here. Now this is the molecule of cis-2-butene. You can simply see here the 2 carbon atoms with a double bond in it, right? And the methyl group that is attached to 1 carbon, and of course a hydrogen that is CH bonding, CH3, CH, then again that is bonded to with the double bond. This is a double bond, right? It is bonded to this carbon with the CH again over here, and then again a methyl group. Now you can see the methyl groups. Now the double bond, there is a barrier to rotation. You cannot rotate them. It's very difficult to rotate to break the pi bond, right? This is one point that has to be kept in mind when we are dealing with these isomeric forms, that is cis-2-butene or Z2-butene. Now it is called cis-2-butene or Z2-butene. Now one thing to note about is that the hydrogen atoms, both the hydrogen atoms are on one side, and the methyl groups, the 2 methyl groups on the opposite side of the double bond, right? On the same side of the double bond. They are on this side, right? So they are not on the opposite side. They are on the same side of the double bond, not on the opposite side, but on the same side of the double bond, right? So that's why it's called cis-2-butene or Z2-butene, and it has got a greater boiling point. So we have learned here the 2 points. Now you have to keep the points one by one in your mind. So these are the most important points, that it has a greater boiling point, and it's called cis-2-butene or Z2-butene. And you can see in the model also that methyl groups are on the same side of the double bond, right? They are on the same side of the double bond. The methyl group, you can see, and this is the double bond. It's on the same side. Whereas if we talk about the other form, is trans to butene. Now we have again a beautiful molecular model. So now this is called a trans to butene or E2-butene. E2-butene. One and the same thing again. Now what was that Z and what was that E? I will tell you in next few minutes. So now let's look at the model of the trans to butene, the isomer, right? The trans to butene. Now here simply you can see the model of trans to butene. Now here you can see that the methyl groups, that is this one, this methyl group, and this methyl group, this one. The methyl groups are on the opposite sides of the double bond. That is this one. You can see this one and this one. They are all both on the opposite sides. One over here and one up, and this one down. This one down and this one up. So they are on the opposite sides of this double bond, carbon to carbon double bond. So this is called trans to butene, and it has got a lower boiling point, right? It is you can simply see it is also called E2-butene or trans to butene, which is this one, right? Trans to butene or E2-butene. So now, up till now, we have learned about, the position of methyl groups, that when they are on the same side of the double bond, they are called cis-2-butene, right? When the 2 methyl groups are on the same side of the double bond, they are called cis-2-butene, right? This one. Whereas when they are on the opposite sides of the double bond, they are called trans to butenes, right? Simple, easy, and very interesting, and so beautiful. Just look at the model, how beautiful it looks. This is the molecular model, right, which you will only see in the videos. So right now I'm showing you, I've prepared this for my viewers so that they can see, right? So that's it. These are the 2 models. I will keep them here. They will simply slip, but I will still try to manage them so you can look at them easily. Okay, so let's proceed further. Now, if we talk about the connectivities, right? So the connectivities are like that, the methyl group. I will show you also methyl group bonded to CH, right? And then CH is doubly bonded to another CH, and then again CH is bonded to CH3. We can look at here easily over here. That is CH3, that is this one. This CH3 here is bonded to CH. Yes, CH is bonded to CH, right? And then this CH is doubly bonded to CH again. Yes, this CH is doubly bonded to this CH. Yes, and then CH is bonded to CH3. Now this CH is again bonded to this CH3. Yes, correct, perfect. So we have seen the connectivities, how they are connected. So in spite of their similar connectivities, the difference lies in the way their constituent atoms are arranged in space, and that's why they are called stereoisomers. Okay, because of the arrangement of atoms, the way they are connected to each other in space, they are called stereoisomers. That is, so we were simply seeing that how the methyl groups were bonded to CH, and then again CH was bonded to CH, and then that CH is again bonded to the CH3. So it's all the game of the connectivities, right? Now, as I just mentioned it to you, that that because of their similar connectivities and the difference lies in the way their constituent atoms are arranged in space, and that's why they are called stereoisomers. That is identical connectivities, and difference lies simply in the spatial way the atoms are arranged, right? The difference lies in the spatial way. Way the atoms are connected. Spatial way the atoms are connected, right? So now we can see that cis and trans to butene are both stereoisomers. That is, of course, and you can see that as they are stereoisomers, they are called cis. They have the cis and trans forms. And now, if we talk about the E and Z, what is E and Z stands for? E and Z, what it stands for? So I will tell you. E equals to horizontal strokes. That is what? Higher priority groups. It refers to higher priority groups. And are on opposite sides. Whereas when you talk about Z, that is Z, Z equals to Z, Z, and that is equals to what it refers to? Same side. Same side, right? Same side. That is, higher priority groups are on the same side. What same side? Of course, it refers to again the higher priority groups are on the same sides. That is Z. Okay, and E equals to the horizontal strokes. That is, higher priority groups are on the opposite sides. Fine. Whereas Z stands for Z, that is same side. Higher priority groups are on the same side, as in cis form. They are on the same side. That's why it's called cis form. And E, that is this one. It's that the higher priority groups are on the opposite sides. Now again a question comes in our mind. What is this higher priority? Higher, and what are these higher priority groups? What does we mean by higher priority groups or the lower priority groups, right? So this is again something new. So E stands for the antigen, right? And Z stands for zusammen, right? Antigen and zusammen. So these are the two terms which I thought I must tell you, and these are the meanings of these two terms which I just mentioned with the help of these molecular models. Now let's proceed further. Now you know what is E and what is Z, or what is Z. Now we'll draw the cis and the trans forms, cis-2-butene and trans-2-butene. Whereas the other form is trans-2-butene, trans-2-butene. And this is the cis form, cis-2-butene. Now we have another example also in which I'm going to attach different halogens so that I can let you understand, I can make you understand what are high priority and groups, right? And why they are called high priority groups. So let me draw the next molecules for you people. So there's a molecule now. Let me draw. With 4 different groups attached to it. Okay, chlorine, and bromine, and of course fluorine and hydrogen. Now if we just simply break the molecule from in between, now we have the number 1 carbon and number 2 carbon, right? So we have these now 4 groups: bromine, chlorine, hydrogen and fluorine. Now if we talk about the higher priority groups, so here in this case the higher priority group is this bromine. It is called a higher priority group. Why it is called higher priority group? Because it's on the, and it is on the first carbon, right? Carbon number 1, the bromine atom is attached. And why it is called the higher priority? Because bromine has higher atomic number than fluorine, that is this one. It has got higher atomic number than fluorine. Higher atomic number than fluorine. Bromine has higher atomic number as compared to this one, that is fluorine, right? So that's why it's called a higher priority group. And whereas at this side, chlorine is the higher priority group. This one, it is the higher priority group. Okay, because chlorine has higher atomic number as compared to hydrogen. Chlorine has higher atomic number as compared to hydrogen. Chlorine has higher atomic number as compared to hydrogen. That's why it is called the higher priority group. Whereas here in this case, bromine has the higher atomic number. So that's why then fluorine, this one, so it's called the higher priority group, right? So this is now another new thing which you have just followed, that why do we call them the higher priority groups. Now here the chlorine was on the second carbon atom, right? This is the first carbon atom, this is the second carbon atom, and it has the higher atomic number as compared to hydrogen and across the double bond. Whereas here the bromine atom, it has got the higher atomic number as compared to fluorine, right? That is carbon number 1 and it's attached to carbon. Okay, so another important way to explain the groups, higher priority groups. Okay, now this is it, and I make the other one also. See, so now here the higher priority groups are A and C. They are higher priority. Higher HP means higher priority groups are on the opposite sides of the double bond, right? On the same side of the double bond, right? So it is called Z. It is called Z. When high priority groups, when high priority groups are on same side of double bond. So that's it, right? This is called the Z form, the Z form, right? Whereas if we talk about this one, it is called E. Now I told you Z stands for Zusammen and E stands for antigen. So it is E. E. That if high priority groups are on opposite sides of the double bond. This is it. That is, this is a higher priority group and this is the highest priority group according to our statement, that they will be on the opposite sides of the double bond. They will be on the opposite sides of the double bond, where here in this case they are on the same side of the double bond. Here they are on the opposite sides of the double bond. So this is the main difference between Z and E? Now, you can easily answer anyone what is Z and what is E. Now, this is all about, geometric isomerism. It is all about what? Of course, the geometric isomerism, which is we are calling it as a cis-trans isomerism, when there is a barrier to rotation around the carbon-to-carbon double bond. Now there is simply a barrier to rotation. If you try to rotate it at about 180 degrees rotation, it would be very difficult, right? You will not be able to rotate it, right? The cis-to-butene, okay? If you do the 180 degree rotation, it becomes very difficult. Interconversion does not occur, and at the ordinary temperatures also. This thing is also that, and at the room temperatures or at the ordinary temperatures, the rotation around the carbon-to-carbon double bond is very difficult. You need to elevate the temperature. The temperature has to be elevated for rotations to occur. For rotations to occur, you need to raise temperature. At ordinary conditions, the rotations do not occur, right? So this, the E and Z or geometric isomerism, the concept of this was, brought to us by Can-Ingold Prelog system, right? And this, especially when we are talking about the geometric isomerism, when there is a barrier to rotation around the double bond exhibiting two different sides to the structure, polarities are arranged using Can-Ingold Prelog system. Now, Can-Ingold and Prelog were the three scientists, right, who explained this concept of E and Z systems, right? And Z stands for Zusammen and E stands for Antigen, right? Now, if you try to rotate this, methyl and this CH, the rotation is very difficult. Now, if I draw this rotation, what I mean by this rotation is this, that if this is the molecule, right? C double bond C, H and a CH3, and of course H and CH3. Now, if you try to rotate it, that is, try to rotate it like this, this goes there and this goes there, right? So the rotations are very difficult, or you can say the 180 degree rotation is not possible, right? So because now these two forms, that is the cis and the trans to butene, they do not interconvert. Both these forms, they do not interconvert at you can say at relatively high temperatures, right? So this comes to our mind that this internal rotation must be yes, of course, the internal rotation is slow. It's very slow, so this is the reason for such an internal rotation to occur. Now, this was something very interesting aspect which I've just explained. Now, as you know, the bonding is energetically very much favorable, and of course the orbitals, that is the 2p orbitals on these carbon atoms, on both these carbon atoms, they must be twisted. They must be twisted away from, their existing phase, right? That is, the pi bond must be broken. Pi bond should be broken. But because now the bonding is energetically favorable, so lack of it is energetically costly. So now more energy is required to break the pi bond that is already available under the ordinary conditions. So what happens at the pi bond in these alkenes? It remains safe, it remains intact, and internal rotation does not occur about the carbon-to-carbon double bond. Whereas if we talk about the single bonds, that is ethane, if we talk about ethane, if we refer to butane, I mean the single bonds, the rotations can easily occur because there is no breakage of the chemical bond, right? So this was something very knowledgeable today. So today you learned about the two configurations of 2-butene, that is the cis and trans stereoisomers of 2-butene, right? And these are the molecular configurations. These are the forms of the molecule that are only, different from each other in the spatial arrangement of their atoms. When we are referring to 2-butene. That is, the two configurations, they differ only by the internal rotations, right, of their atoms. So I hope today you like this video regarding cis and trans isomerism. You learned a lot about what is cis form, what is trans form, right? This is the cis form, this is the trans form, and internal rotation. I mean, there's a barrier to rotation, right? Around at 180 degrees. If you rotate the molecule to 180 degrees, I mean, it's simply interconversion does not occur as at the ordinary temperatures. You need to raise the temperatures, and as it has to do with the 2p orbitals of each carbon atoms, they must be also twisted away from that existing copolarity, right? So we have learned a lot. I hope you like this video and you will learn about the cis and trans isomerism in detail. That is a geometric isomerism. We call it geometric isomerism, and I have also explained you the examples of 1-butene and 2-butene. So please, now it's your duty to learn by comparing with the molecular models. Also, these are the beautiful models which I've just prepared, right? And you've learned a lot from these models today. I hope you like it. Thank you very much.